In a couple of previous modules, we had seen the fitting of general linear model to datasets. We have also checked how to correct for the assumptions of the linear model. In this particular module, we will look at an example dataset which is available with the software package R, and we will see how the multiple linear regression model is fitted to the data, how the estimates of the parameters involved are calculated, and we will also look at the interpretation of the same. In a previous module, we have seen some applications of general linear model in the form of regression, in the form of analysis of variance, and in the form of analysis of covariance, depending on what kind of explanatory variables we are dealing with. In case the explanatory variables are all continuous, we have a multiple or a simple regression setup. In case we want to perform analysis of variance for different categories, we have x's in the form of dummy variables which segregate the data into different categories. And in case of a combination of both ANOVA and regression, we have a combination of categorical as well as continuous x variables, which gives rise to the ANCOVA model. One such special case which we talked about was regression model. So when we have one independent variable and one dependent variable, we fit a simple regression model. And sometimes when the number of dependent variable is 1 and independent variable is more than 2, then we fit what is called a multiple regression model. Also, before fitting a linear regression, we have seen in one of the previous modules that there are a number of assumptions that need to be satisfied. After satisfying all those conditions, if we know that they have been fully taken care of by the assumptions that we make, we fit a multiple linear regression model to the dataset. Here in this module, we will discuss the fitting of such a multiple linear regression, the estimation of the concerned coefficients, and also the testing of significance of those coefficients using the statistical software R, and we will also use the Galapagos data set which is available readily in R for the use of the reader. So the general form of a multiple linear regression where we have k different independent variables would be of the form y equals alpha 0 plus alpha 1 x1 plus alpha 2 x2 plus alpha k xk plus the error term which happens to be the random part in the model. Now given that we want to fit such a data, let us look at an example concerning the number of species of tortoise on the various Galapagos Island. There are 30 cases, as in there are 30 observation points, and there are 7 variables that have been measured. So first, when we read the data into R, we can see what the data set looks like. So we first have the name of the species, and then we have the frequencies for each of the species. We have the endemics, the area from which they have come, the elevation of that particular area. We have the distance with the nearest neighbor. We have screws and the adjacent measures taken for this particular data set. Once we have read the data, we can see that the frequency of species, that is our response variable or the variable of focus. We would like to predict how many of each of the species that we have named in the data set will belong to which area, and what features of those area, what geographical features of those area would influence the increase or decrease in the number of that particular species. In order to do that, we need a predictive tool. And before we can come up with a robust predictive tool, we would want to fit a statistical model. So fitting a linear model in R is done using the LM function. The LM function specifically fits linear models. In case we have a data set where a linear model when fitted violates a lot of the assumptions that we make in a linear model case, we have to make transformation either of the variables, or we sometimes choose to use a different set of models which are not linear per se in terms of the parameters, but they are called generalized linear model, but we will discuss that in a separate module. Here we will discuss the use of the LM function in fitting a multiple linear model to the Galapagos dataset, which you will find in R under the name Gala, Gala. In the next few slides, we will show the fitting of the model and how the algebra of least square works in case of a multiple regression model. On the next slide, I have used the LM function to fit the data where the species factor has been regressed on area, elevation, nearest, screws and adjacent, and the data set has been mentioned specifically to be the Gala data set. After we have fitted the data using the LM function, the next R code tells us that we can find the summary of the fitted model. So after the model has been fitted and we look at the summary, R gives us as output the following sets of information. First, under call, we will see the formula which R has used to fit the regression model, taking species as the dependent variable and all the remaining 6 variables as its independent. And it is also specifying the dataset that we are using. We have the residuals or the summary measures of the residuals that we get after fitting this regression model. We are looking at the summary measures. First, under call, you will find the formula that R has used to estimate the equation to fit the statistical model to the data. And then we have the 5 summary measures for the residuals in terms of the minimum, the maximum and the 3 quartiles, the first, the third and the second, where the second happens to be the median of the set of residuals that we get after fitting the regression model. Now underneath we have the coefficient table where first they have listed the list of x variables, and corresponding to each of these we have the estimate of the corresponding coefficients. So let's take the first value 7.068, which happens to be the intercept. So in a model where we have y equals alpha 0 plus alpha 1 x1, alpha 0 happens to be 7.068. Taking the next value, corresponding to area, the coefficient is negative 0.0239, which means that the alpha 1 attached to x1 happens to be this value, given that x1 is the area. And the remaining estimates of the coefficients have similar interpretation. Now if we talk about interpretation of coefficients, the values here will give us the amount in which y is going to change for a unit increase in the corresponding x. In case of simple regression where I only have one x, then the change in 1 unit of x will reflect the change in y by the amount corresponding to the estimate of the coefficient. But in case of multiple regression, where I have several x variables, when I am changing one of the x's by a unit, the others have to be considered constant for us to look at the estimate of the coefficient and tell that this is the amount by which y is changing when x is changed by 1 unit, holding all the other x's constant. Also at the bottom we have the significance codes. If you look at the last column of the output, it's the probability or the p-value corresponding to each of these coefficients. So after the estimates, we have the column which gives us the standard error, and then we have the t-value column, and finally we have the column for p-values. The p-values help us test the significance of these individual factors, in the sense that if I have 5 or 6 coefficients in the form of alpha 1, alpha 2, alpha 3 and so on, we test whether the corresponding x variables are significant in the model or not by testing the null hypothesis alpha 1 equals 0, alpha 2 equals 0 and so on. And this hypothesis is tested by looking at the p-values which are given at the last column. If these p-values happen to be less than our fixed level of significance, we reject the null hypothesis and we accept the null hypothesis otherwise. In this case, you see at the end of the table where we have the p-values corresponding to 2 p-values, which is for elevation and the last one is for adjacent, we have the p-value significant at a level of significance 0.001. However, all the other p-values are much larger than a standard level of significance of 5%, which means that the model that we had fitted has a significant factors as elevation and adjacent. The other factors of area, nearest and screws which were initially added into the model were not significant and hence can be dropped from further analysis. Also, after the significance codes, we have the residual standard error, that is the whole standard error after fitting the regression model to the dataset. We have the degrees of freedom 24. In addition to that, we have multiple R square. Multiple R square happens to be a measure of how good the data is fitted by using the given dataset. A multiple R square of 0.7658 tells us that almost 76.5 or 77% of the variability in the frequency of species has been explained by the variables that we have taken as our independent variable. However, after this model fitting, we've seen that two of these factors are significant and the others are not. So maybe a good idea would be to only select the significant factors and fit the model again, in which case we will expect to see a higher multiple R square, which will tell us that the factors which have now been chosen in the model are significant and they will explain a bigger amount of variability in our y variable than the current set of 5 factors. Finally, at the last line of the output in R gives us the F statistic value for a corresponding degrees of freedom 5 and 24 and a corresponding p-value. Now, what is the purpose of this F statistic? We have already tested the individual significance of the factors that we have included in the model. In case of a multiple regression setup, instead of checking for all the other significant factors individually, we also want to look at the overall goodness of fit of the model. In order to do that, we use the F statistic and the corresponding p-value for this particular statistics is also given to us. As you can see, considering 0.5 as the level of significance that we want to use, the p-value happens to be much lower than the given level of significance, so we can reject the null hypothesis that the overall model was not a well-fitted model. So rejecting that null hypothesis would mean that the fitted model, although not all the factors were significant, overall was a significant one in predicting the frequency for the different species based on the 5 independent variables taken into account. Now, a lot of important quantities have been identified in the R output. Other statistical packages tend to produce output quite similar to the one which we are seeing in case of R. However, one useful feature of R is that it is possible to directly calculate quantities of interest. It is not necessary here because the LM function does the job, but it is very useful that the statistic you want is not part of the prepackaged function. Because the LM is a very standard canned program which is already available in the R packages, we can use this and fit a regression model, the summary of which will give me all the important outputs or all the important measures required to perform the test and estimation of fitting a linear regression model. But in case we want to measure in case we want to calculate any one of the measures or any one of the parameters separately, we can do so in R as well, as we will demonstrate in the next few slides. Now, because of the ease with which we can compute useful functions in R, we will also demonstrate the algebra of least square. Now, according to the algebra of least square, which dictates that given the linear model form of y equals x beta plus error, the least square estimate of the parameters is given by beta hat equals x prime x whole inverse x prime y, where beta hat is the vector of all the estimates of the coefficients which are involved in a multiple regression model. X happens to be the design matrix or a collection of the columns where each column is the value of the different variables taken as the independent variables in the model. And y is the vector which contains the observed values of the dependent variable. Now, this form of beta hat comes from the normal equations which are of the form x prime x times beta equals x prime y. These are called the normal equations, and solving these we get the above form of the estimates of the beta coefficients. In order to use these functions in R and find the values of the coefficient estimates, we perform the next few steps. First, we make the X matrix and the response Y. So we have a data frame which is called the Gala. It's available in R, so we define our X or the design matrix and the y vector or the response vector as follows. So x equals C bind 1 Gala minus C1 and 2 will only retain the x variables excluding the names, the first two columns, which is the names of the species, and the second is the frequency of the species. And y equals Gala dollar species will only take the frequencies, which is taken as the response variable or the dependent variables. Now we construct the matrix x prime x, which we will need later on to find the estimates of the beta. So T function does the transpose and the asterisk does matrix multiplication in case of R. So in order to find x prime x, we first find transpose of x and then we take a matrix multiplication of this with the x. However, when we try to perform this function, R gives us an error in the form that it requires a numeric or complex matrix or vector argument form for R to carry out the above mentioned function. Now, what does this error tell us? The problem here is that matrix arithmetic can only be done in R with numerical values, but x has been defined or derived from the data frame type. Gala, as I mentioned, was a data frame already available with R. We have only segregated a few of these columns and considered them as x, where x is still considered as a data frame by the software. So data frames are allowed to contain character variables which would disallow matrix arithmetic to take place, and hence the error. So what we need to do is we have to force x into the matrix form by using the following functions. So we define x equals as dot matrix, where this is the function which defines x forcibly as a matrix. And then after we define x as a matrix, we can find x prime times x, which the output is given in the next slide. Once we find x prime x, we then need to find the inverse of this matrix in order to find beta hat. So inverses can be taken in R with the function solve. So we use solve on transpose of x times x and we get the following matrix, which is an inverse. So we can find x prime x whole inverse in a somewhat more direct way by first fitting the regression model using gfit and the lm function. We call this model as gfit. Now we look at the summary of gfit and save it as gs. After we save the summary, then we look at the covariates, the values of the covariates in the unscaled form by gs $covariate.unscaled. So the output is given at the bottom. You have the different values of the variables which are taken as independent variables in the model, and you have the unscaled covariates. So in particular, the fitted values or the predicted values and residuals can also be looked at by using the function gfit $fit and gfit $residual. In both cases, underneath the function, the output has been given. So for each of the different species, we have the corresponding fitted values of the dependent variable, which is number of frequencies and number of species, and we also have the residual, which is nothing but the value of species which is observed, the frequencies, and the difference between this and the observed values which we have already got by fitting the regression model. In estimating the multiple regression coefficients, the rationale is to minimize the sum of squared errors. In other words, we find the estimates of the coefficient by means of ordinary least square. In some previous modules, we have discussed what the mechanism of ordinary least square methods are. So here we will demonstrate in R how we are finding the estimates of beta. So using the OLS technique, we can get beta hat directly by writing the following functions: x prime x inverse multiplied by transpose of x multiplied by y. So x prime x whole inverse we have already calculated in previously, and we've seen what the results look like in the previous slides. We take the transpose of the x matrix and finally multiply it by the vector of responses, which is y. And the results are given to you in the bottom of the slide. as you will see that by this method, the estimates of the coefficients are the same as we had got from fitting a linear regression model using the LM function. Now, other than the functions which we had used in the previous slide, in case we wish to find the estimate in a more stable form, we can perform the following functions. We can use the solve function over the matrix multiplication of transpose of x times x and transpose of x times y. Also, you will see that in this case as well, the output yields us the same estimates of beta value as we had seen twice previously, first using the function and then using the linear model fitted function. Now, after we have got the estimates of the coefficients, in order to perform the test of significance, which was automatically done in case of linear model fitting using LM, we can perform the same thing by hand, or rather by using a separate function in R. In order to perform the test of significance using the coefficient estimates and the standard error, we need to first estimate the standard error, which can be done in the following way. We can take the square root of the diagonals of x prime x whole inverse and multiply it by 60.975, which, if you remember, happened to be the random square of error in case of the model fitted using the LM function. So after we use this, we get a set of standard errors for the intercept as well as the coefficients corresponding to each of the x variables that we had used. Now, after we get the standard error, we need to first find the value of the test statistic, which is the t-test statistic, taking the estimate of the beta and dividing it by the corresponding standard error. This t-distribution has 1 degree of freedom. We can then either choose to find the p-value corresponding to this test statistic, or for the relevant degrees of freedom and level of significance, we find the critical value from the t-table and compare it to decide on whether that particular beta value or coefficient estimate is significant or not. In case it is a significant model, the corresponding factor or the x variable in the model happens to be significant and otherwise not. So in this particular case, if we separately find the t statistics and test them for the significance of the corresponding x, we will see that we get the same result as we had got when we used the LM function in R previously to fit the model, and we will see that the two factors, elevation and adjacent, in this case will also turn out to be significant. So what we have learnt in this module is, when you have a data set with one dependent variable and several independent variables which are continuous, then taking a cue from the form of general linear model, we can fit a multiple linear regression model to the data set. Once we fit the data set, the purpose of such fitted data is to look at the estimates of the parameters involved so that we can use that model as a predictive tool, and also for the purpose of inference to test for the significance of the variables that we have included in the model. While we fit the regression model, the idea is to estimate these coefficients, and we have seen explicitly using example dataset how such parameters in case of multiple linear regression are calculated either through the LM function in R or through statistical techniques which are available in the software.